Welcome everybody to this new session of the Chilean Probability Seminar. We have the pleasure to have with us a student here, now professor at USACH, Sebastián Barbieri, who is usually not doing probability, but decided to do something fun for a while. He did his undergrad here, then he went to Lyon for 4 years to work at
3 years.
3 years. Yeah, you say 4 years.
No, well,
3.5.
3.5. I did half of a master.
Yes.
Yeah.
And then you moved to Canada.
Yeah.
You went to live with Luis Fredes for a while, 1 year.
Yeah.
And then you come back here, and now you are going to discuss about how one can use percolation for understanding cellular automata.
Thank you. So, well, thank you for the invitation. It's always a pleasure to give a talk to people who are not in my community. It's not that I don't like the people in dynamical systems, but it's, I mean, one likes to have some variation in his life, right? So I want to stress, I come from a different community, so maybe my notation will not be the one you're used to, so please do not hesitate to ask if there's anything you're not understanding. My goal is to make this talk understandable, so please interrupt me as often as you want. Okay, so I'm going to talk about cellular automata and percolation on groups. As you come from the probability community, you're probably used to talking about percolation, or at least you have some notions of what percolation means. So the first part of my talk will be focused on explaining what's a cellular automaton, and where's probability in this thing, and what's the connection with percolation theory. All right? So let me give you some setting. This will be the general setting for my talk. I'm going to consider a countable group G. So you could think of your favorite group here. It could be a finite group. It could be an infinite group like the integers. It could be a regular tree, like, I don't know, the Cayley graph of the free group. Think of any group that you like. This will be one of my ingredients. My second ingredient will be a finite set A. You could think of, say, 0 and 1, two symbols. And I'm going to consider the set of all maps from D to A. Okay, so I have a group, I have a finite set, and I look at all of the possible ways to color my group with symbols from A. Okay, all right, so those will be my basic objects. Now, there are two things that I must give you. So the first thing is that we endow the space A to the G with the natural product topology. So A is a finite set, so here I take the discrete topology, and in A to the G, I just take the product of the discrete topology, right? So convergence in this space means point-wise convergence on every coordinate. Okay? And the second is that we consider a natural action on this space, which is called the shift action, given by, well, just translation. If I have a configuration X and I act by G, and I want to know what's the value in H, it's just G on position G minus 1 H. Okay, and this is for all G, H in the group and for every configuration. All right, so that's my setting. I just have a group. Think, for instance, on the integers, and I color the integers, right, with some, I don't know, with some values on some finite set, like 0, 1, right? So I have the integers, and at every position I have a 0 and a 1. And my action is just shifting these sequences, right? Okay, that's the general setting. So what is a cellular automaton? There are two ways to define a cellular automaton. One that is very beautiful mathematically, and another one that is actually the one that people understand better, but both are equivalent. So I'll start with the abstract one because I like it better. So I'm going to give the following definition. Cellular automaton is a map phi from A to the G to itself, which is continuous with respect to the prodiscrete topology, and it's G equivariant. That means that it commutes with the shift action. For every G in G, if I look at some configuration X and I apply phi, and I shift this thing, this is the same as applying phi to the shifted version of X. Right, and this is for every X. Right, so this means that it is a map which is continuous, and if I shift some configuration, I apply my cellular automaton, it's the same as applying the cellular automaton and then shifting. Right? So that's my setting. That's a cellular automaton. So let me give you an example to make things clear. So for instance, let's take the group G equals Z. Let's take A equals to 0 and 1. And I'm going to consider the following map. I'm going to consider the map phi from A to the Z to A to the Z, given by phi of X at position N is just going to be 1 if there are more ones than zeros in X at position N minus 1, X at position N, and N at position N plus 1, and 0 otherwise. So this is called the majority cellular automaton. So let me show you what it does. Imagine I have some configuration here. So this is X. These are the integers. Say here is position 0. And in every cell, I have a symbol. Right? So 0, 1, 1, 0, whatever you want. All right, and I want to know what is phi of X. So how do I apply this map? Well, I just look at the definition. It says, well, if you want to know what's the value at n, so for instance at 0, you look at coordinates n minus 1, n, and n plus 1. And you say, well, are there more ones than zeros? No, there are 2 zeros and 1 1, so the image here is 0. Right? Next one, 0, 0, 0. Oh, all zeros. I chose a very bad font. But this one is a 1. This one is a 1. This one is a 0, and so forth. Right? Okay, this map, you can clearly check that it's continuous, and it's also invariant under sheets, right? If I just shift my configuration, well, this rule is the same thing. Okay, so that's a cellular automaton. It's this kind of maps. Okay, and as you saw here, this map can be defined in a very different manner, which is the following. I was actually sliding some finite window, checking what's the local configuration, and according to some local rule, I decided how to update this value, right? So actually, that's the reason why these things are called cellular automatons. It's because it's an automaton in the sense that it takes finite information and it gives me something finite, and it's applied on cells in an uniform way. So actually, that's a theorem. Let me write it over here. This is a theorem, not a very hard one. It's actually an exercise nowadays by Curtis, Headland, and Linden. That says that phi is a CA if and only if there exists a finite subset of the group and the map phi from A to the F to A. So it's just a function that looks finitely many coordinates and gives me a symbol such that if I look at the image of some configuration at some position, this is just applying the local rule at the shifted version. All right, so it's exactly what I say here. In this case, I could think of this set minus 1, 0, 1 as my f. My rule is, well, if there are more ones than zeros, I put 1, otherwise I put 0, and I apply this rule everywhere. Right? So you have this. This is a nice thing about cellular automatons. On the one hand, you have this combinatorial description that says, well, you have a finite window and a local rule, and you just apply that everywhere. So it's some kind of uniform map with nice combinatorics. And on the other hand, you have this algebraic description. These are exactly the continuous endomorphisms of the dynamical system given by the sheet. Right?
I have a question.
Sure.
So why is you could do the same thing, but instead of adding the 3 neighbors, you can add 2 to the minus n?
Yeah, as many as you want.
Yes, but then you are not counting infinite.
Oh, no. You're not counting infinite. In this definition, you just want a finite window.
Yeah, but what happens if I sum 2 to the minus n all the future ones?
Oh, you want this thing to be non-uniform.
Yes.
If it is non-uniform, then you lose continuity.
Okay.
You can actually show that it's equivalent. If you have a continuous map, which is G equivariant, this condition is called G equivariant in group theory lingo, then there must exist a finite window. It's just uniform continuity. Yep. All right, so that's an old story, but these are the objects I'm going to be considering. I'm going to be looking at cellular automatons and groups. Okay, so far, any questions? All good? Okay, please do not hesitate to interrupt me. All right, so in general, I do dynamical systems and group theory, so I'm interested in dynamical behavior of cellular automatons and in general dynamical systems. And in this case, I'm going to be interested in ergodic theory. So I'm going to be considering a measure on the space of all configurations. So take mu, a Borel probability measure, on A to the G. Okay, so I take any Borel probability measure on A to the G. Now, what's an example of a Borel probability measure on A to the G? There's one that's quite natural. You just take any probability distribution on the alphabet A, and you take independently, identically distributed overall G. Right? That's one thing that people in probability hate people in dynamical systems for. We usually call those measures Bernoulli measures. And that's a cardinal sin for some people in probability. So, well, you'll have to forgive me if I do that. Okay? Okay, so I'm going to write this very, very small so you can't see. So whenever I say Bernoulli measure, I actually meant that. Okay? The identically, okay, never mind.
IID.
Yeah, IID measure with marginal nu on every coordinate. Okay. All right, so that's when I say Bernoulli, that's what I actually mean. So forgive me, it's just what people do in ergodic theory. Okay, so I'm going to present two different dynamical properties that a general dynamical system could have, and I'm going to study that in cellular automatons. One is going to be a property related to chaos, and the other one is going to be related to order. Okay? To define them, I'm going to need a particular set. So given a CA5 in a group.
Yeah. ¿Puedes usar un plumón que no sea el naranjo que no se ve, por favor?
Okay. So here it says chaos, and here it says order. Okay, so given a cellular automaton phi, given a configuration, and given a finite set F, I'm going to define the following thing. I'm going to define C of X F bar phi as the set of all configurations such that for every n, if I look at the iterates of X restricted to F and the iterates of Y restricted to F, they are the same. Okay, so what's the idea? Imagine that I have the integers, and this is my little set F. So what I'm looking is at all of the initial conditions, all of the Y, such that when I look at the evolution of this thing, phi of Y squared, etc., I always see the same evolution that X would see on this whole cylinder. Okay. So essentially, I see the same behavior restricted to this finite window. So using this set, I'm going to define a chaotic property, an order-like property, and I'm going to do it right here.
Sebastián,
Yeah.
this F that you are, it's not the same that the one that you used to define the local rule, right?
Not at all. It's
Okay.
an arbitrary finite F.
Okay, thank you.
Yeah. Yeah. The local rule is implicit. I give you a cellular automaton. I don't even need to define a local rule. I could just say it's a continuous equivariant map. Okay. All right. So my chaotic property is going to be called sensitivity to initial conditions. And my order-like property will be called equicontinuity. And these are both going to be properties with respect to a Borel probability measure. So let me give you the definition. I'm gonna say that CA is sensitive to initial conditions with respect to a Borel probability measure mu if there exists a finite set such that almost everywhere the measure of this set C X F bar phi is 0. So what does this mean? It means that there exists a finite set such that with probability 1, if I take some random initial configuration, then the measure of this cylinder set, the ones that actually look the same, is 0. So that means that if I make perturbations far away, eventually I see some difference here.
So this is for all X, or all X, mu almost.
No. There exists a finite F such that mu almost everywhere, and the almost everywhere, it's here. So I usually write it like mu of the X such that is 1. But this is shorter because I have less space.
I mean, just another way of saying it, you would say the expected value of the measure of C is 0.
Yes, that's another way of saying it. Yeah. So, but I prefer to present it this way because this other property has some symmetry with respect to this one. I'm going to say that cellular automaton is equicontinuous with respect to this measure mu if for all F finite we have that mu almost everywhere for X, this thing is positive. So what does this mean? It means that if I take some random configuration with respect to this measure, and I look at the space of configurations that stay the same for all its history, this is for all natural numbers, then it has positive measure. There's actually some cylinder set. Well, there is an analog of the Lebesgue density theorem for the Cantor space, so it's a Cantor space. So this means that there's a cylinder that actually remains here with positive probability, a cylinder with positive probability. Okay, so these two things are kind of similar, and they kind of look one like the negation of the other, but it's not, right? These are two almost sure things. So if I negate this, it's, well, this has measure. It doesn't mean that it has measure zero, right? But it kind of looks like they are opposites, right? This is chaos. If I do random perturbations far apart, well, my behavior eventually diverges in a very small set, finite set. With continuity, it's the opposite. My behavior is really, really predictable. There is a whole cylinder where I never see differences beyond some finite region, right? Okay, so questions so far? Okay, so now I'm going to introduce a theorem. It's an old theorem. It's a theorem from from 87. It's a theorem by Gilman. This is a theorem by Gilman on 87, and it says the following: take G equals Z, let phi a to the z, a to the z be a CA, and mu be a Bernoulli measure with my definition of Bernoulli. So an IID measure on every coordinate, you know. Then either phi is mu sensitive or phi is mu equicontinuous. So one or the other, right? It means that there's nothing in between. Either I am sensitive to initial conditions almost everywhere, otherwise I'm equicontinuous almost everywhere. Okay, so it's kind of nice. I cannot have behaviors in between. I cannot have anything that's kind of, well, in some part of the space I am very sensitive to initial conditions. In other parts of the space, well, no, I look equicontinuous. No, it's either one or the other, right?
So I think just a small question. So
yeah.
I can imagine a lot of things that's sensitive to initial
like
conditions, just the sheet. But continuous things apart from the identity, I don't have any.
Well, there are a lot of examples. An easy example would be a permutation of the alphabet.
Okay.
Right, a permutation of the alphabet. Well, same thing. But you could also have some things that have some movement, but it stays bounded. Actually, in general groups, it's easier to define equicontinuous CA for some reasons that related to torsion and stuff like that. Okay, any more questions so far? So this is an old theorem from 87. And what we wanted to study is, well, what happens if I take other groups? So our question is, what happens for other groups and for other measures? Okay. So we did two things in our paper. First, we generalized this theorem of Gilman to a large class of systems and to a large class of measures. And second, we characterize the groups where this kind of dichotomy holds. Okay, so let me present our results, and then I'm going to tell you a little bit about the group and what's the connection with percolation theory. By the way, I did not ask. I have until 5:20.
Yes.
Yeah, okay, that's fine. All right. So let me tell you what's our theorem. Theorem 1. So we generalized Gilman's theorem in two directions. First, we took it as far as possible with this group, and we changed this Bernoulli measure for any ergodic measure. So our theorem is, let G be a finitely generated group, which is, I will explain, virtually Z. No, actually virtually cyclic. Let mu be an ergodic measure on A to the G. Then every CA is either mu sensitive or mu equicontinuous. All right, so, well, lift your hands. Who doesn't know what a virtually cyclic group is? Great. Okay, so everybody knows what a finitely generated group is, right? Okay, there's a finite set of elements in the group such that every element of the group can be written by multiplying these guys. Okay, so virtually means there exists a finite index subgroup which is cyclic. So essentially it means that geometrically this looks like a cyclic group. And what's a cyclic group? There are two possibilities. It is either a finite cycle or the integers. So what this means intuitively is that geometrically my group looks either like a line or like a point. A finite group, or it contains a finite index copy of the integers. Okay? All right, so that's not a big increase, right? Actually, from saying Z and saying, well, finite groups and things that are virtually cyclic, it's not actually a big difference. The proof is essentially the same. But there's some difference when if I take ergodic measures. It makes the proof slightly more complicated, but not that much. Oh, lift your hands. Who doesn't know what it means for a measure to be ergodic? Okay, you know that. Okay, good. Okay, so, well, the Bernoulli measure, by my definition of Bernoulli, is ergodic, so this is a generalization. Okay, so it holds for any ergodic measure, actually. All right, and my second theorem, or second theorem, sorry, is the following. Let G be a finitely generated group which is not virtually cyclic. Let there exists a CA on an alphabet A to the G such that, let me give it a name, such that phi is neither mu equicontinuous nor mu sensitive with respect to a Bernoulli measure, with the uniform Bernoulli measure, with respect to the uniform Bernoulli measure. So uniform Bernoulli measure is just in every coordinate I take a uniform measure, right? So even with respect to this measure, which is kind of the simplest that one can define here, there is a counterexample. And there is a counterexample for every group which is non-virtually cyclic. Okay, so that's our theorem. And let me give you actually the broadest theorem, because this is just for finitely generated groups. This part is not hard, but it looks nicer. If I say that a group satisfies the Gilman's dichotomy, I mean that this happens. So our big theorem is the following. Let G be a countable group. Yeah. Was there a question?
Yeah, I have a question. You describe the virtually cyclic groups as either being like essentially equivalent to the line or being finite. Did I understood it correctly?
Yeah.
And
So
how, sorry, just let me finish the then how does equicontinuity works or in the finite groups, right? Because X is always contained in CX.
it's trivial. The dichotomy is trivial on finite groups. So that's why
Okay, it's trivial.
in writing cyclic. Actually, the real theorem is virtually set, and it's interesting for infinite groups. The case of
Okay,
finite groups is trivial, but we just study it because we can.
okay, thank you.
Yeah, yeah. The dichotomy holds trivially in finite groups because it's always equicontinuous. All right. So let's see the accountable group. The theorem is that G satisfies Gilman's dichotomy if and only if G is not, and I'm going to say three bad words, locally, virtually, cyclic. Oh, I always do this wrong. No. Yeah. Okay, so I said what virtually means. Not virtually. Oh. Yeah, thank you. If only if G is locally virtually cyclic. So I explained what virtually means, having a finite index subgroup isomorphic to a cyclic group. And I have to say what locally means. Locally just means every finitely generated subgroup is virtually cyclic. And it's quite easy to show this. It's just because cellular automatons, as they are defined by a finite window, they always act on some finitely generated subgroup. So it's kind of easy to go to countable groups using that. If you want to move beyond countable, you have measurability issues. Okay? But that's a big theorem. So we have a full characterization of the groups that satisfy Gilman's dichotomy. All right? So I've talked for about 30 minutes, and I still haven't said the word percolation. So what's a connection with percolation? The thing is that to prove this part, theorem 2, we used a big theorem on percolation theory. And actually, your CA, the CA that we give as a counterexample works because the fact that these groups, the ones which are not virtually cyclic, have a non-trivial percolation threshold. Okay, so I'm going to talk you a little bit about percolation and what's the CA that I'm considering. Okay. So what's the connection with percolation? So now I was thinking about introducing percolation, but let me know if I'm being too obnoxious. If you already know what percolation is, tell me to hurry. Who doesn't know what percolation is on a graph? Great. Then somebody will listen. Okay, so I'm going to talk very quickly about percolation from the viewpoint of someone that does group theory. Take a graph. Take a countable graph B. I'm going to talk about site percolation. I forgot to say that. And consider the space zero, 1 to the B. So essentially, I mark every vertex with a 0 or a 1. And I want to interpret zeros as vertices that are gone and ones as vertices that remain. Okay? Given x in 0, 1, B, we say that x percolates if the subgraph induced by the V in B such that x in B is equal to 1 is infinite. All right. There's no measure so far. I'm just taking some vertices. This is the same as saying, well, I take a subset of the vertices, and I say that that subset of the vertices percolates if, well, the reduced result graph has an infinite connected component. Sorry, has an infinite connected component. Yes, I did. Connected component. Yeah, that the other thing was false. Incorrect. Okay, so now if I take a measure on this space, take mu over L probability measure on 0, 1 to the B, and I say that mu percolates if the measure of the set of all B x in 0, 1 to the B, such that x percolates is positive. Okay, so that's percolation with respect to an arbitrary measure. All right. The probability that with respect to this measure, I take some vertices, the probability that there is an infinite connected component is positive. Okay, and now if we denote mu p, the Bernoulli probability in 0, 1 to the B, such that mu p of some configuration at any position being 1 is equal to p. This is very bad notation, but anyways. If we denote mu p as the Bernoulli probability, where the marginal is just 1 has probability p and 0 has probability 1 minus p, then we can parameterize this with this here, right? And we can observe the following, right? If I take p is equal to 1, then this measure is supported on the O1 configuration. And if B is an infinite graph, then of course it percolates. If I take p equals to 0, then it's supported on the O0 configuration, and of course it doesn't percolate. And this is an increasing event. So, well, at some point I have 1, at some point I have 0. There must be some position where I transition from 0 to positive. Okay, so we can define the percolation threshold as follows. It's called PC of this graph. And it's just the supremum of all p in 0, 1, such that mu p does not percolate in the graph B. All right. Okay, so this is a very interesting number. If you take, for instance, the integers z and you take the Cayley graph, it's just an infinite line. The percolation threshold is going to be 1, right? Because if with some positive probability you kill some vertex, well, you disconnect everything. So you end up only with finite components, right? And it's actually a very interesting thing to read about the percolation threshold for Z squared. That's a half, and it's a very nice computation, right? Okay, so let me tell you a few things about this. If I look at my graph as a metric space, the actual value of the percolation threshold is not really important. Well, in some cases it is, but actually, if I just care that this percolation threshold is not 0 or 1, this is an invariant of quasi-isometry. So it is stable under most geometric transformations of the graph. In particular, if I take a group and I change the set of generators, the fact that this number is strictly between 0 and 1 it does not depend on the generators. Okay, so let me just say that. We say the percolation threshold of a group is non-trivial if the percolation threshold of the Cayley graph of G with respect to some set of generators is strictly between 0 and 1. For some generating set S. All right, and this does not actually depend on the set of generators. So I could here I could put for all generating set S. Okay.
Do you recall the definition of the Cayley graph?
Yes. The Cayley graph of a group is the graph where the set of vertices is given by the group, and the edges are of the form G, GS for S a generator. So essentially, I connect elements of the group if I can move from one to the other by a generator on the right. Okay. Okay. So that's percolation. Everybody on the same page? Okay, this is side percolation. There's also bond percolation where you put the probability on the same definitions. And yeah. So there's a really nice theorem. This is a really, really nice theorem by 5 people. So Dominique Copin. And this is just one person. Goswami. No, I have to put them on order. Goswami. Raufi. Severo. Yeah. He's the one that actually kept working on percolation a lot afterwards. And Yadin. Mariel Yadin. Yeah. And it says the following: they characterize the finitely generated groups with non-trivial percolation threshold. So a finitely generated group has non-trivial percolation threshold if and only if it is not virtually cyclic. So it's exactly the same that we use on the other theorem. All right? Yeah.
No. Z is an example.
Yes, Z is an example with trivial percolation threshold, and it's actually a cyclic. Right?
And that's right.
And which one is not?
Right. Yeah. Well, that one is, I was just thinking.
Yeah, it doesn't.
That's a good example of one direction.
Yeah, right. So let me tell you a little bit about the story. Actually, proving this theorem for groups of like Z or abelian groups or in general groups of polynomial growth, it's not hard. Proving it for groups of exponential growth, it's actually not hard either. The problem was that there are groups which have sub-exponential growth. And that was a big open problem, and they solved this using the Gaussian free field and some really nice techniques. Nowadays, Severo and some other people, Panagiotis and I don't know who else, gave some elementary proofs of this that I can actually understand. But it's a really nice theorem, and actually it doesn't just hold for groups, it's for quasi-transitive graphs of superlinear growth. Okay, so it's a really nice theorem. Okay, so that's percolation on groups, and this is the theorem that I'm gonna use. So again, what's the connection? That's what I'm gonna tell you in these last 15 minutes. Well, the connection is we use that monstrous theorem from probability theory, and we constructed a cellular automaton, which is neither mu equicontinuous nor mu sensitive, and it uses this machinery to show, right? So we simulate percolation with this cellular automaton somehow. Let me tell you how it works.
That's for your second theorem.
Yeah, for my second theorem. So the first theorem is actually quite...
That's what you said was sort of extending.
Yeah. So finding the counterexample was the hard part. The other part, I mean, it's technical, but you kind of know it's true. I mean, if it holds for Z, it's kind of easy to imagine that it holds for virtually set groups. And generalizing to ergodic measures, well, you just look at the proof and you say, oh, okay, if I just use point recurrence theorem in a nice way, it obviously works. So it's actually not hard. But this other part, well, the hard part is coming up with the example and figuring out what the connection with percolation is. So, and the interesting thing is, This is just an example. If we were able to give an example through other means, which is not percolation, it would give a very nice connection to this theorem, right? This had a very, I mean, at least for me, non-trivial proof using the Gaussian free field at first. So it would be a nice connection if we had some other way of constructing this counterexamples. Okay, let me tell you what the connection is. And for that, I'm going to define what the counterexample actually is. Okay. The example more than counterexample. So let G be a finitely generated group and fix a finite set of generators. I'm going to define the following alphabet. A is going to be 0, 1 times 0, 1 to the s. So I take a component which is just the symbol 0 and 1, and for every generator I also take a 0 and a 1. Okay? I identify A to the G with, well, 0, 1 to the G times 0, 1 G times S. Sorry, 0, 1 S to the power of G. It's obvious, right? If I just put to the power of G, it's the same thing. And we take the following CA. Well, if I identify my alphabet as these two components, 0, 1 to the G and 0, 1 to the power of S to the power of G, I could think that the elements here are actually pairs. X, W, where X is in 0, 1 to the S, 0, 1 to the G, and W is in 0, 1 to the S to the G. Okay, and what's my CA gonna do? On the second component, it's gonna do absolutely nothing. So my second component is just there for some reason I'm gonna explain later on. And in the first component, I'm just gonna take the additive average of all of the values around G, but only if the edges parameterized by W are open. So let me write the formula and I'm gonna explain. I'm gonna take the sum over all generators of W in position G, position S, X in position GS, and I'm gonna do this mod 1. Sorry, mod 2, sorry. I should have left some space for this. Okay. I take this sum mod 2. So what's the intuition?
You mean that it's just like an indicator function. You are not doing.
Sorry? What?
So it's just a product because you're in 0, 1.
Yeah, it's a product. It's a product. So let me tell you what's going on. I have my graph. Right? So G, I have the Cayley graph, GS. So here imagine I have some element and I have all of the neighbors by S. S1, S2, S3, S4, S5. So my W is giving me numbers here, right? 0, 1, 1. Essentially, for every position G, there's a value associated to every generator. So I can think that those are zeros and ones on the edges, right? And it works on every direction. Here I might have another element, and coming back, well, this edge is open and this one is closed. So this is a directed thing. Okay? And I also, this is W, and I also have numbers on the edge, on the vertices, right? Here I might have a 0, or a 1, a 1, a 0, 1, 0, 1. So what does my CA do? Well, on the edges, it does nothing. It keeps that. On the vertices, well, to update this position, I look at all my open neighbors. I look at all the values here, and I sum them up too. Okay, so it's an average on a random subgraph. It's random directed subgraph with the randomness on the edges. And here it's additive. Okay? All right, so...
Sorry, I'm confused. What is being summed? I can see.
So, everywhere. At every position G, to update the position X in G, I look at all of the neighbors. I look at the edges. If they are open, I sum this thing, and then this sum I take it mod 2.
X is the value of the vertex.
Yeah. So I don't necessarily take the value of the vertex unless I say that the identity is a generator, which I could do.
Yeah, no, but on the neighboring.
Right. Yeah.
What do you mean by open edge?
With a 1. So I mean open. Open means W in G S is equal to 1.
Just to see if I understand, essentially you take your graph,
yeah,
and to each edge and to each vertex you put a percolation in both vertices and edges.
Except that I'm gonna interpret percolation only on the edges.
Yes. So, but at the same time, the only thing you're moving is going to be on the vertices and the random subgraph.
The randomness in the edges just keeps like that. I take it as something behind, as some environment, and my CA is only acting on the vertices. It's only updating the position of the vertices.
Yes,
okay.
It's updating it through the percolation.
Yeah, exactly. So, all right, I have this CA. It's nice. I defined it like that. A priori, there's nothing probabilistic in this thing, except the fact that I mentioned percolation like 2 times in the intuition, but it's just a CA, right? It's just a formula. It's actually algebraic on the first component if I keep the second one intact. It's linear. So how do you prove that this thing is neither mu sensitive nor mu equicontinuous? The fact that it is not mu sensitive is easy. Why? Well, if I take any big finite subset of my group, I could just put 0 on the edges that go outside of this thing. I put zeros on all the edges that go outside from this region or inside. And then I take this big cylinder set. Well, if I do changes outside, it's never going to come in. Right? So that shows that it is not mu sensitive. Okay, so this is a very short scheme, right? How do I prove that it's not mu equicontinuous? Well, in fact, it might be mu equicontinuous for some S. And here's where percolation comes through. I can show that if I take here the uniform Bernoulli measure.
I got lost. Why do you? Because you just need to find one. Yeah. Set F, one deterministic, but your set F is deterministic. So how can you fix that you have zeros outside?
Oh, no. So to negate the fact that I'm mu sensitive, I would have to say for all F. Well, I take some F. I put zeros outside, I take that cylinder, and this set is just going to have positive.
So you say that, okay, this one has positive.
Yeah. So that proof is actually, you can do it directly. It's really not complicated. The other part is complicated, and in fact, it does not work for every generating set. In fact, we need to choose a generating set such that the percolation threshold of the group is less than a half. That's not really that important, but if we want to take the uniform measure here, it's important. Okay, and there are 2 things that go into this proof. The first is we actually can show that if we take the infimum over all generating sets of the percolation threshold of the K graph, this is 0. So you can take the percolation threshold as little as small as you want by changing the generating set. This, I always thought that it should be trivial for people in probability theory, but it was really hard for me to prove. I actually had to use techniques from group theory, like separate the case into amenable groups and non-amenable groups, and use Strassen's theorem on one hand, on the other one, a quasi-tiling theorem by Orsten and Weiss. So if you know an easy proof of this, let me know. But it's quite intuitive that it works. But if you try to do the computation, you get a lot of correlations that I really couldn't manage. But well, it is true, I proved it. And this goes into the proof. And the other part is that you can take the evolution. If you put a 1 at the origin and you look at how it affects other vertices under a random configuration, you can couple that with side percolation on the group with respect to the same set of generators. And couple it so that there's percolation on one side, this one goes arbitrarily far, if and only if you have percolation on the other group with probability. So you put those two things together. If you have percolation with parameter at most a half, then that would mean that if I flip a bit from 0 and 1 on arbitrarily far positions, there's always some positions that eventually affect the origin.
However, isn't that just you take G as the generator group?
In massive finite.
Oh, okay.
Okay, this is really bad notation.
The way you do it is you build new edges between 2 points, but you build them in an intelligent way.
So the intuition is the following. You take big balls on the group as you're generating set. So it's really hard to disconnect your graph right now. But trying to prove that it's actually not that easy.
Okay. Yeah.
Okay. Anyways, so the idea is the following. You will have positions arbitrarily far that affect the origin with high probability in some set of positive probability where you percolate. And, well, you can pick many configurations here. And if you want the behavior to be the same on some finite set, well, it must coincide on infinitely many coordinates. And that's an event with probability 0. So essentially, with that computation, you can show that this thing is not mu equicontinuous for big enough S such that the percolation threshold is smaller than a half. Okay, I know this was extremely quick, but I was trying to fit into the time. So that will be all. Yeah.
Why did you use the Dominic and company?
Oh, because I actually need my my percolation threshold to be at least a half. I think I said it the wrong way.
Okay,
at least a half.
of course, anything.
Yeah. I want it to be small. Sorry, at most a half. I want it to be small and smaller than a half.
Yeah, but so to prove that you're used.
Yes, because otherwise this thing is 1. For set, this is 1. Oh yeah. This theorem is for these groups.
Yeah, of course.
Yeah.
No, but okay. I guess my point is, if you're using that in the proof.
Oh no. The only thing that we're using is that if we have a group like this, then it has a non-trivial percolation threshold. And we can find a new set of generators such that the percolation threshold is smaller than a half.
I mean, yeah.
And that's it. And then we couple the aside percolation exploration process on the group with a process that we induce with this thing. We make 2 events have the same probability in that coupling, and that's how we go from one to the other.
Thank you.
Okay.
Are there any questions? This means it's natural to extend this for other measures which are not IID. Like
I have no idea. You mean finding a counterexample with respect to that measure?
So the only thing yes.
I don't know. I mean, the connection with percolation certainly does not seem to work, but I don't know. Maybe.
And is it the only case like percolation? So what, for example, like imagine that you have a measure which you almost. Well, I don't know what makes almost surely don't percolate because it makes no much sense here. But
I mean, you could define percolation as I did, right, with respect to any measure on the state space of Earth.
Yeah. But now you have like 0, 1. So this is where you have. So okay. So essentially, like, can you show that if that certain measures still do satisfy? But because, for example, here you could say if the percolation threshold is bigger than 1/2, then you could imagine that the uniform case here. In fact, it does not percolate. So then does this mean always that you are, what's the term? The term is ordered. I cannot remember that.
So my answer is I do not know. I don't know. I think Felipe Garcia Ramos asked that question when we were discussing this paper, and we reached quickly the conclusion that we had no idea. And we didn't want to keep pursuing that. But it's a nice question. I don't know.
Because intuitively, what in a way you are saying is that there is a family of measures, and in a way, in which you have a threshold or not. Like
This, but it's a quite natural family. But yeah, of course, you could consider different families, Markov measures on these things, harmonic measures. There's quite a lot of families of measures where it might be interesting, but I don't know.
so the
Presumably, if you take another field,
Another what?
another cellular
Oh, yeah.
which sort of, I guess what you need is that it depends on a big
Yeah.
box, then the same would be true.
So we tried several different variations of this. One where you actually updated things looking at sites. We couldn't manage to prove it for those. So it's just that the technique kind of worked precisely for this case. Now my expectation is that it should work for many variations of this. Actually, I think it should work for some reversible cellular automatons. This one is not reversible. It's not bijective as an action on A to the G. But I think this thing could be adapted so that you have a reversible example, a bijective CA. That's my feel, not a proof. I have some ideas of how to do it, but yeah.
if you take the Laplacian in the first coordinate instead of
So what do you mean Laplacian? The sum of all guys that are around?
minus
Minus the guy, but that's
minus the guy in
okay. But that's you could simulate here by just saying that the identity is a generator. Summing one is the same as subtracting one, so that's the Laplacian.
So in a way, you're solving the heat equation.
Yeah, so yeah, I'm doing PDEs finally.
You're solving the heat equation in the graph.
Yeah. When I was a student here, I never liked PDEs. Now I'm doing PDEs in a very weird way.
Solving the heat equation in the random graph is what it's giving you there.
Yeah.
So other questions on the chat? If not, here we are going to start eating, but before let's thank Sebastián again.
Thank you. ¿Cuál proceso? Para que siempre